draw coloring. So we can just start by coloring in our halogens.
We have like 5 minutes to do this.
You can have, I don't know that I'll give you a full 5 minutes for coloring, but I'll give you like 3 minutes for coloring. Yeah. Today we're going to be learning about the halogens. Now, the important thing to understand about the halogens is that this group is basically the complement to the alkali metals. So it pairs really nicely with the alkali metals, and oftentimes, if you remember what the alkali metals can do, you can remind yourself what the halogens do, because there's just like lots of ways in which they're similar, in which they complement each other. Yes, Joaquin?
What should I title it?
Halogens. So today we're going to learn the properties of the halogens. Because the halogens are non-metals, we're also going to talk a little bit about the properties of non-metals in general. We're going to color in column 7A, which is our halogens. And we're going to find the charges of things in this group and make sure they're marked. All right, so first thing to note about the halogens. Our alkali metals were metals. Our halogens are going to be non-metals. These two groups, they oftentimes complement each other. When it comes to the properties of non-metals, a lot of these are going to sound familiar because they're just a little bit different from what the metals did, right? So while the metals were on the left-hand side of the periodic table, the non-metals are going to be on the right-hand side of the periodic table, with the exception of hydrogen, which is a little bit weird, being a non-metal on the left-hand side. While the metals had high melting points, and so tended to be solids at room temperatures, the non-metals are going to have low melting points and will likely be either liquids or gases, with a few exceptions, just like the metals had a few exceptions at room temperature. Yes, Gabby?
Is the charge
For the halogens, the charge is indeed -1, yes. Yossi?
What should we title this?
Today's lesson is the halogens. Now, while our metals formed ions that are what? Anyone say it with me? Positive, yeah. So our metals form positive cation ions. Our non-metals, like the halogens, form anions that are going to be negatively charged, because the metals like to react by losing electrons, while the non-metals like to react by gaining electrons. So y'all see how these groups complement each other? The metals could do ionic bonds or metallic bonds. Non-metals can do can do ionic bonds, and they can do covalent bonds with other non-metals, but they can't do metallic bonds. So covalent bonds are only accessible to non-metals, while metallic bonds are only accessible to metals, right? And ionic bonds will usually involve a metal and a non-metal joining together. There's lots of other properties of metals that you can see have complements. We talked about how metals tend to be malleable and ductile. We can draw them out into wires or like hammer them into thin sheets, right? While our non-metals are much more likely to be brittle, to break or shatter if you hit them, right? Our metals were conductive. They would really easily transfer things like heat and electricity. Our non-metals tend to be insulators that don't conduct heat or electricity well. Yes, Nayan?
So it's like when during the copper tape thing, that's why we put the tape over to insulate.
Yeah.
This tape thing.
Oh, that's a good question. I'm not, okay, so actually I probably can't answer this. Tape is a type of plastic. Plastic is made out of hydrocarbons, so it probably is a mixture of carbon, oxygen, and hydrogen. The exact chemical formula, I have no idea, but I would put good money on those 3 elements being the most common elements in whatever the chemical formula is for the plastic that makes up tape. And yeah, it is non-metals, which is why it's such a good insulator. All right, so metals and non-metals can serve as complements to each other, and in particular, the alkali metals and the halogens serve as really good complements to one another. So take a moment, think about these elements. Tennessine is one that is like synthetic. There's no like actual chemistry that's going to involve it because it only exists very briefly in laboratories. But the rest of these exist in nature, and you've probably encountered at least the first 4 of them. So my question to you is, raise your hand if you can tell me about a time when you know one of these elements has been used. All right, so Shep, what's an example of one of these elements in use?
Chlorine for pools.
Yeah, we stick chlorine in pools. The goal of the chlorine in the pools is to kill things in the pools, right? It's a disinfectant. It sterilizes the pool. It keeps things like algae from growing. Lisa?
And toothpaste?
In toothpaste. Fluoride is in toothpaste. Fluoride will sometimes also be in mouthwash. Fluoride also goes into our drinking water, at least if you live in a city. And it helps prevent tooth decay by killing bacteria and helps make your teeth stronger. I actually grew up in a part of the country where we did not have a centralized drinking water system. I got my water as a child from well water that was drawn directly from the groundwater. And so the water I grew up drinking did not have fluoride added to it. And because of that, I had to get special dental care. I had to go in once a year and they would take a little tray and fill it with fluoride paste. And I'd have to sit there with it in my mouth for a long time to treat my teeth with fluoride because it wasn't something I was getting in my water, right? So fluoride can help keep our teeth strong by preventing things like tooth decay that are caused by bacteria. Now, one side point I want to make about this is when you think about stereotypes of people from rural parts of the country, what's one of those stereotypes that might be relevant here? Yossi?
Is that the stereotype of like kind of broken old teeth?
Yeah, broken or rotten teeth is a really common stereotype about people from rural parts of the country.
And that's because of the fluoride?
It's because fluoride in the water system is a government service that all of you who grow up with access to city water have access to without even thinking about it, right? It's a part of your healthcare that is just done for you. And every time you drink water from the tap or from the water fountain, or every time that you boil pasta in water that you got from your sink, you're getting a little bit of dental care that people in large portions of this country don't have access to unless they go way out of their way to get them. So when we think about some of the stereotypes that exist about people from certain parts of the country, take a moment and think about where those stereotypes come from. Because oftentimes, they come from active disinvestment by the government. Services that you all take for granted that people from other parts of the country might not easily have access to. Yes, yes.
Are the halogens acids?
The halogens are capable of forming strong acids when they bond with hydrogen cations. We will get to that later.
So is that kind of why,
So just the ion here,
dirt away?
fluoride in something like toothpaste is being used to help kill bacteria and protect your teeth. It doesn't have the hydrogen cation, which is the thing that makes it an acid. So in that particular dental care thing, it's not serving as an acid. Acids are not great for your teeth.
Okay.
What other examples? We've got fluorine, in particular the fluorine ion, fluoride, in tooth care things. We've got chloride in for cleaning pools and stuff. Talia?
Why do they all end in INE?
That's like a naming convention for a lot of elements. Many elements will end in INE, especially if they were discovered later on in chemistry. A lot of the elements that have more normal names are things that were named before we really put them on the periodic table. Anyone know of any uses for bromine or iodine?
Is it iodine in Vaseline?
Oh, I don't know if iodine is in Vaseline. It does show up in healthcare related things though. Jacob?
Can iodine kill you if you drink it?
Yeah.
And I have a bottle of it in my bathroom.
So what is the bottle of it in your bathroom for? Do you know? I mean, it definitely has a purpose. I can tell you what it's probably for.
I don't know, it's just in there.
And the fact that it could hurt you if you drank it is intimately connected with what it's for. Because what iodine is for is it's a disinfectant, right? So if you've ever gone to a nurse or a doctor or a pharmacist and you've gotten a shot and they've taken a wipe and the wipe is brown and they wipe your skin, and you can see that little like brownish, yellowish residue, and then you get the shot. There's two different wipes that people might use. If they're clear, then that's probably an alcohol wipe. If it's brownish or yellowish, it's probably either bromine or iodine, both of which can be used as medical disinfectants. And the goal there is basically to kill bacteria on the skin so that when you have a shot, you're not transferring bacteria from outside of your body to inside of your body, because your skin serves as an important barrier. The main job of your skin is to keep the outside outside of you and your insides inside you, right? It's what skin's for. I'm not going to call on this because I know it's off topic, Emily.
Well, you're gonna threaten us again.
How many of you are backpackers or have ever gone hiking on like a multi-day thing? All right. Some of you might be familiar with this. You might not, depending on what you use. But have any of you ever used iodine to purify your water? Or do you use filters or boiling or something?
Drink it,
All right, so those pellets, do the pellets have a color to them?
Oh, like,
All right, if they're white, they're probably chlorine tablets. If they are brownish or yellowish, they're probably iodine tablets. When I used to lead backpacking trips, because I would take groups of a dozen like college freshmen out into the woods on the Appalachian Trail for a week before they started university, and when we did this, we used iodine to purify our water. And what we do is you have like a Nalgene, a 1 liter bottle of water, and you put 6 drops of iodine in there, shake it up, let it sit for an hour, and the iodine would kill all of the bacteria and protists and giardia and things that can potentially be harmful in it. So the thing that all of these descriptions of the halogens have in common is they're all toxic. Yeah, Talia?
Well, if it's all toxic, then why do we drink them?
Great question. With any kind of poison, it's the dose that makes the poison. So 6 drops of iodine diluted in a liter of water is going to do absolutely nothing to humans, but it'll kill giardia, which is a protist that can give you really bad diarrhea, right? So you don't want to have giardia setting up in your guts. The iodine will kill them because they're teeny tiny creatures, right? Whereas you're a very large creature, the amount of iodine that you would have there wouldn't be enough to kill you. If you were to drink iodine straight, that would be a very bad idea, and you'd want to call poison control for sure. Joaquin?
So like, could you theoretically like drink enough like tap water to like not have to brush your teeth?
No. You should brush your teeth, because there's also like physical buildup on your teeth, and you should also floss your teeth. I will say, as somebody who like went to who lived in a part of the country where appropriate dental care is not something everyone can take for granted, having bad teeth is like a pretty significant detriment to your quality of life. It really impacts how people treat you when you have bad teeth, which isn't fair and isn't right, because most people with bad like don't have beautiful teeth. It's purely a result of like financial systems and government disinvestment in their like the areas that they live in. It's not things that those people have done, but people absolutely will be pretty intensely prejudiced against folks with bad teeth.
Why?
Right?
Oh,
so is giardia and stuff like in the water naked? Because whenever my family goes there, we drink the water. My family says not to drink the water there.
Giardia and similar protists are the things that cause like traveler's diarrhea, yeah. And you could disinfect the water with iodine if you wanted to. All right. So, the thing that all of these halogens have in common is that they're disinfectants. They're disinfectants because they are so intensely toxic. These things are poisons, and it's the fact that they're poisons that makes them useful to us. Right? So we have all of these different uses for them. The next thing I want you to do is I want you to take a moment and either on your table or in your notes, preferably in your notes, go ahead and draw me a planetary model of fluorine alongside a planetary model of chlorine. And I want you to tell me what these two elements, both of them halogens, have in common. Some questions you might want to have in your mind as you're doing this are things like, if they form a covalent bond, how many bonds could they make? As well as, if they form an ion, what would the charge of that ion be? So take a moment and think basically about how these elements are likely to form bonds. All right. Let's move forward. So, when you drew these, you should have ended up with things like this. And when I looked around the classroom, it looks like folks were on track. So for fluorine, it's element number 9, so 9 protons. Its atomic mass rounds to 19, so 19 minus 9 protons gives us 10 neutrons. And of course, with those 9 protons, it has 9 electrons, 2 in that innermost electron shell. I am not going to be picky about whether you pair up the ones in the innermost shell or do north and south. Either way is fine with me. But for the second shell, you can see we have 7 valence electrons. How many of them are unpaired?
One.
Yeah, 1 unpaired valence electron. Raise your hand if you can tell me, what does it mean to have 1 unpaired valence electron? What's relevant about that? Shep.
Doesn't that mean it loses one when it bonds?
Not that it loses one, it could share
One bond.
right? So if it can share a single valence electron, it means it's capable of forming 1 covalent bond, right? So for covalent bonds, it could share and make a single bond. For ionic bonds, what does that mean? Lisa?
That means that we'll be really, really, really happy with the alkali metals because those form anions instead of cations, which the halogens do.
You flipped your cations and your anions.
Oh yeah,
But yeah.
Sorry.
While the alkali metals are +1, what's the charge of the halogens going to be? -1, right? Because we have 7 valence electrons. They want to have 8. You jump like 4 steps ahead, which is excellent. So we've got 7 valence electrons. We want to have 8. So for ionic bonds, fluorine and chlorine are going to want to steal a single electron. Shep?
Why on the first electron shell did it bubble up? Aren't you supposed to be
I'm not going to be picky about whether you do this with that. So that first electron shell can hold 2 electrons, right? And there's basically 2 different ways that different teachers teach this. Some teachers say, hey, these 2 electrons are partnered to each other, so we should draw them together. And I think that's a reasonable approach and a good approach. The other approach is to say, hey, we want to make sure that folks are in the habit of always going, 1 in each quadrant before we make any pairs. So let's do north-south so that you remember not to put things together until after you've got, 1 in all the quadrants that are available. I'm not picky about which of those 2 ways you do it. So if you'd drawn those 2 electrons as north-south, or if you drew those 2 electrons as 2 together, I'm not going to mark you wrong for either of those options, because that's not the thing that's terribly important. Yossi?
Would something like beryllium be able to pair both of those together or something like that?
If you had beryllium, oh, this is a great question. What you're basically asking is, can you form an ionic compound where you have 1 cation and 2 different anions?
Yeah, is that possible?
That is, weirdly enough, not a thing that tends to happen.
What
would happen instead is beryllium would pair with 2 fluorines, or it would pair with 2 chlorines, because beryllium has a charge of +2, and fluorine and chlorine both have a charge of -1.
Which would it be more likely to?
Oh, let's talk about that. So, what Yossi's question boils down to is, which of these 2 elements is more reactive? So to answer that, let's think about the alkali metals. With the alkali metals, we said, oh, these things become reactive by losing electrons. So the easier it is for them to lose an electron, the more reactive they're going to be. So for the metals, as we went down the periodic table and we had bigger and bigger and bigger atoms, the larger metals are more reactive because metals react by losing electrons, and the bigger you are, the more far away that 1 valence electron is, the easier it is to let go of it. But non-metals, they react by stealing electrons, except for hydrogen. So if they react by stealing electrons, is it going to be easier to steal an electron as this like massive atom where the electrons are really far away from the positive oppositely charged nucleus? Or are you going to be more reactive if you're tiny and you're tight and you're a really small atom that just wants to grab an electron. Lisa?
This explains why fluorine is really reactive.
Bingo. Fluorine is the most reactive nonmetal on the periodic table because it can just grab a single electron. And it's really small, so that electron is pretty close to the nucleus, which makes it easier to grab it. Because remember, electrons are negative and the nucleus is positive, right? So for metals, the bigger you are, the more reactive you are.
But why
For
not,
nonmetals, the smaller you are, the more reactive you are.
but why not hydrogen?
Because hydrogen reacts by losing an electron, which is more similar to the metals than to the nonmetals. Yeah, hydrogen is a weird element in many
Is that
ways.
why hydrogen is kind of on the opposite side?
Yeah.
Okay.
Emily. Hydrogen is not conductive on its own. Pure water is not conductive. You need an ion in there in order to make water conductive, actually. Like salt water or pool water or something is very conductive because it has other things in there, but water on its own is not. So, from these planetary models, we can gather that the halogens are all going to form anions with a charge of -1, right? They're always going to form anions with a charge of -1, and that means they love to form bonds with things that have a charge of +1. So as Lisa said, that means these guys are going to love the alkali metals. All right, we talked about some of this yesterday. Yesterday when we talked about the alkali metals, we said, hey, the alkali metals love to react with the halogens. When they do this, they form a salt. So an alkali metal plus a halogen gets a salt. But the alkali metals are not the only thing that has a charge of +1. Hydrogen can also form cations with a charge of +1. If a halogen anion reacts with a hydrogen cation, so a hydrogen cation and a halogen anion, that gets us a strong acid. So once again, the halogens are serving as a complement to these alkali metals. The alkali metals could react with hydroxide to form a strong base, while the halogens react with hydrogen to form a strong acid. And then remember, hydrogen cations and hydroxide anions, those are the two pieces of water. Water is made out of a hydrogen cation and a hydroxide anion. So the halogens can react with the hydrogen part and they make strong acids, while the alkali metals can react with the hydroxide part and they can make a strong base. Yes?
Do we know the formula for a stomach acid?
I think that your stomach acid is sulfuric acid. I could be wrong on this. I think there's multiple different types of acids. Sulfuric acid is H2SO4. So SO4 is sulfate. It's a polyatomic anion, which means it's made out of multiple elements, but we treat it as though it's a single anion. And we treat it like an anion with a charge of -2.
Yeah.
And then the cation there is hydrogen. So once again, it's something that adds hydrogen into the solution. Things that add hydrogen into a solution are acids. Things that add hydroxides into a solution are bases. We're going to talk about this in more detail tomorrow. Right.
Will it ever pull in the oxygen to become a strong base rather than?
No, a halogen wouldn't. No.
Okay.
So halogens can either react with metal cations, any metal cation. It doesn't actually have to be an alkali metal plus a halogen is going to be some kind of salt, which remember is a broad category in chemistry. Or they can react with hydrogen to form strong acids. So we've got a bunch of different kinds of strong acid. We have hydrofluoric acid, which uses fluorine as the anion and hydrogen as the cation. We've got hydrochloric acid, which uses chlorine as our anion and hydrogen as our cation. Hydrobromic acid, hydroiodic acid, and hydroastatic acid. All of those are strong acids, in the same way that the alkali metals could all make strong bases. right? So once again, these two groups really complement each other. And remember, water, imagine water as an ionic compound with these two ions. The hydrogen cation, if there's extras of these, you have an acid. And the hydroxide anion, if there's extras of these, you have a base. If what you have is both things in equal measure, if there's equal amounts of each, then you're just going to get water, right? They'll bond together to make water. All right, we've already talked about the reactivity of these things. Remember, the smaller the halogen, the more reactive they are. And that is it for today's lesson. So y'all are clear to start today's class kit.